This is Climate Watch. I'm Zhao Ying. Welcome to the show. China is on track to become the world's largest generator of nuclear energy. The China Nuclear Energy Association says the country currently has 60 nuclear power units in operation and 36 under construction. Another 16 units have been approved and are awaiting development. The combined capacity will be around 125 gigawatts. The capacity under construction accounts for more than half of the global total. In the meantime, China has signed on to an international pledge to triple global nuclear energy capacity by 2050. The decision was announced at the Nuclear Energy Summit 2026 in Paris. Brazil, Italy, and Belgium also signed the pledge, bringing the total number of signatories to 38. So how is China growing from a nuclear newcomer to one of the world's largest generators of nuclear power? How is nuclear technology evolving? And what is driving this renewed global momentum behind nuclear energy? Joining us now is Professor Zhao Jiyun from the Department of Mechanical Engineering at the City University of Hong Kong. Professor Zhao, thank you so much for being with us.
Yes, it's my great pleasure.
So we are seeing a growing number of countries sign on to the goal of tripling global nuclear energy by 2050. What is driving this renewed global interest in nuclear right now?
It is essentially a response to the carbon neutrality targets, energy security, and the rapid expansion of the digital economy. As of March 2026, 38 nations, including major economies like USA, China, Japan, UK, and France, have endorsed the declaration to triple their nuclear output by 2050 compared to the 2020 levels. Firstly, nuclear power plays an important role to meet the carbon neutrality targets. Nuclear power is stable and weather independent, economically competitive, and near zero operational carbon emissions. While wind and solar are vital, their intermittency creates a critical need for firm 24 hours baseload power to keep grids stable without emitting carbon. Secondly, the energy security. The fuel costs only occupy about 10% of the total electricity generation costs for nuclear power plants, while it can be over 70% for fossil fuel-based power plants. So therefore, nuclear power is not sensitive to fuel prices and is offering a stable domestic buffer against the wild fossil fuel price swings. The Ukraine war was a massive wake-up call, exposing the extreme vulnerability of countries that rely on imported fossil fuels. Thirdly, the explosion of AI and data center capacity has created unprecedented need for reliable, high-density energy. Technology giants like Amazon, Google, and Meta are no longer just passive consumers. They are actively signing multi-decade deals to restart reactors or fund next-generation projects to secure their own carbon-free power supplies.
Yes, but actually we know that in China for a decade after Fukushima, the nuclear energy was always discussed with safety and caution in mind. But in recent years, we are seeing the word accelerate appear in government documents. So do you see a shift in how China thinks about and manages nuclear programs?
Oh, yes. While safety is still the baseline, I see the shift for nuclear policy in China in recent years. Besides the drivers we just talked in the previous question, carbon neutrality targets, energy security, and the rapid expansion of the digital economy, it has other drivers in China for this shift. First is the technical confidence. For years, China was busy in absorbing foreign designs and perfecting its own. Now, the domestic advanced Generation 3 designs with enhanced safety features, named Hualong 1, is being mass-produced. Unlike the Generation 2 designs, such as reactors in Fukushima, which use active emergency cooling, Hualong 1 deploys both active and passive emergency cooling, with significantly improved safety. Second is the engineering capability. China has very strong capability to build up nuclear power plants faster, cheaper, and better. Currently, the cost to build up a nuclear power plant in China is only about 20% or less of Western's. Thirdly, Currently, the nuclear share of electricity generation in China is still very small, only about 5%, while it is 65% in France and 19% in the USA. Even in the whole world, it is about 9 to 10%.
So, how important is nuclear energy for China's carbon peaking and carbon neutrality goals? Like, is it essential or is it perhaps just one of the several options?
Nuclear energy is no longer just one of many options in China. It has become essential for the dual carbon goals. The reasons are first, renewable energies such as wind and solar are intermittent by nature, but nuclear provides a steady, high capacity power supply. As China phases out coal, nuclear is the only carbon-free technology that can match coal's reliability to keep the industry grid stable. Second, we are seeing a shift where nuclear isn't just for electricity anymore. It's being used for comprehensive utilization, providing industrial steam and district heating. This is vital because the heavy industry is one of the hardest sectors to decarbonize, and nuclear heat offers a direct solution that solar and wind cannot easily replicate. Finally, looking forward to 2060, the consensus is that to achieve 80% non-fossil energy, China needs a massive scale-up of nuclear energy. Current projections suggest nuclear will need to provide about 18 to 20% of total power.
Yes, and also as you mentioned earlier, AI has become a key driver for nuclear energy because we need to build those AI and data centers. But when it comes to these, data centers, what advantages do nuclear have compared to, say, wind and solar?
Oh yes, AI is becoming a significant driving force for nuclear expansion. The big data centers run 27, which demand incredibly massive and stably supplied power. The international hyperscalers such as Microsoft, Google, and Tencent are not just buying renewable credits, but they are also actively seeking power purchase agreements with existing nuclear power plants and even restarting retired ones. The big advantage of nuclear electricity over wind and solar is mainly reliability and power density. Solar and wind are intermittent. You need huge battery banks or backup gas to keep a data center running through calm, cloudy days. Nuclear provides constant, carbon-free baseload power in a relatively smaller footprint. For key AI infrastructures that cannot afford downtime, the always-on nature of nuclear power is a game changer. The upcoming technologies, such as the small modular reactors, provide a promising solution to the campus-side edge energy system, which renders a dedicated and customized power source for distributed data centers.
Yes, and we know that China is expected to become the world's largest nuclear power producer by 2030. So, how did the country transition so quickly from relying on foreign technology to becoming a global leader in this field?
The development of nuclear technology in China is a very legendary story. The journey of China's commercial nuclear power started from 1980s, firstly by importing technology from the foreign countries such as France and Russia. But what changed the game was a very deliberate multi-step strategy, learn by building, standardize, and innovate. China didn't just buy reactors instead of insisting on technology transfer and local manufacturing. With each new unit built, Chinese engineers gradually grew up with better established experience, and the domestic supply chain got stronger. In 2000s, China imported AP1000 from Westinghouse. Instead of just replicating it, the Chinese teams absorbed the design, improved on it, and eventually rolled out its own Generation 3 design, the Hualong 1. The other big piece is consistency. While some countries went through boom and bust cycles, China stuck to a steady and long-term plan. This allows it to build fleets of the same reactor type, bringing down costs and construction times. Now, China is not just building the most reactors, but leading in the Generation 4 reactor field. So the story is a mix of patient learning, smart standardization, and policy stability.
Yeah, let's first look at the third generation designs. You mentioned the Hualong 1, which belongs to the third generation models. So, can you tell us how do we define the third generation model and why has China standardized around them at this moment?
The third generation reactors, like Hualong 1 or AP1000, present a major step up from the earlier Generation 2 models. The biggest progress is safety. The Generation 3 reactors are featured by the well-designed passive safety systems. In the emergency, the Generation 3 reactors basically utilize the natural circulation and gravity to safely and effectively take away the enormous heat and cool down the fuel assemblies. The operators or external power are not needed anymore, which fundamentally reduce the risk for repeating Fukushima accident. By standardizing a few proven Generation 3 designs, the country can speed up the construction of multiple units, streamline the supply chain, and significantly bring down the cost. This also makes the upfront investment more predictable and export easier.
Yeah, and also, as you said, China is also experimenting with multiple fourth generation reactor technologies, from high temperature gas cooled reactors to the thorium molten salt reactors. Can you explain what makes a reactor fourth generation?
Oh yeah, the Generation 4 nuclear technology includes six types of advanced reactor designs, which focus on sustainability, safety, economics, and proliferation resistance. The only nuclear fuel can be found in the nature is uranium-235, which has limited reserves and can be used up within about 50 years. So therefore, one of the key tasks for next generation or Generation 4 reactors is fuel sustainability, which can transmute uranium-238 and thorium-232 to nuclear fuel for thousands of years urine. So in addition, Generation 4 reactors aim to be even much safer than Generation 3 reactors, not only preventing fuel meltdown in accidents, but also operating more efficiently. For example, in high-temperature gas-cooled reactors, the graphite-based pebble fuel elements are used, which never melts down, and the high-temperature helium is used as coolant, which provides high thermal efficiency for power generation and high-grade heat for industrial applications. So in the thorium multi-salt reactors, the thorium 232, which had plenty of reserves in the nature, will be converted to uranium 233. Uranium 233 is the very good man-made nuclear fuel.
Yes, you mentioned this thorium based molten salt reactor. It actually has received a lot of attention right now. Can you explain more on this? Like, how transformative is this technology breakthrough?
Oh, the technological breakthrough is revolutionary. Unlike other reactor types, which use uranium as fuel, the thorium-based molten salt reactor converts thorium-232 to uranium-233 as fuel. So the uses molten salts as coolant. Typically, thorium is dissolved in a molten fluoride salt mixture, usually lithium fluoride and beryllium fluoride. As thorium has plenty of reserves, much more abundant than uranium on Earth. It is very helpful for fuel sustainability. Using liquid fuel eliminates the fuel melting accidents such as 3 Mile Island and Fukushima accidents. It enables water-free cooling, therefore, it does not need to be built along coastlines and can be deployed directly in deserts or inland areas. China achieved the world's first thorium to uranium fuel conversions in 2025 and remains the only country operating this type of reactor. This technology breakthrough is very important in China. It will shift the nuclear fuel from reliance on imports to self-sufficiency. So while over 70% of China's uranium supply relying on imports, the thorium resources are abundant in China. The reserves ranking among the highest in the world. Moreover, most of China's thorium deposits are associated with rare earth mining, making the cost extremely low.
Yeah, so I understand that in a traditional reactor, water is very important. Like if the water stops flowing, you have a crisis. But in a molten salt reactor, this will no longer be the case. So does this mean China will soon unlock its inland nuclear development in the near future?
Oh, yes, it is correct. In traditional water-cooled reactor, loss of coolant flow means loss of cooling for the fuel, which can lead to the core meltdown. In a typical molten salt reactor, the fuel is already in the liquid form and dissolved in the molten salt coolant. So if the reactor overheats, the freeze plug equipped at the bottom of the core will melt, and the fuel will drain into a passively cooled holding tank, where the reaction stops automatically. So this eliminates the risk of a catastrophic core meltdown. So as it does not require large volumes of water for cooling, it can be built in the inland areas, including dry areas like deserts.
Also, the high temperature fourth generation reactors can produce heat at much higher temperatures. So, beyond electricity, what kinds of industrial processes could this heat power?
The high temperature thermal energy has very broad industrial applications. For example, it can be used to drive thermochemical cycles to achieve efficient hydrogen production. It can be used in the thermal desalination processes for seawater desalination. In the petrochemical industry, the reactor can replace fossil fuels to provide high temperature heat for refining processes. Also, for industries like steel and cement manufacturing, nuclear heat can directly take the place of coal and natural gas.
Yeah, and also we know that China has this three-step strategy, moving from thermal reactors to fast reactors to fusion. And fusion is often called humanity's ultimate energy. Why is that?
Yeah, thermal and fast reactors are fission reactors. The energy is produced through the fission of heavy nuclei, such as uranium-235, caused by neutrons. Thermal reactors operate with slowed or thermal neutrons, while fast reactors operate with fast neutrons. The uranium mined on Earth contains about 0.7% uranium-235, and the remaining about 99.3% is uranium-238. So the odd atomic mass number isotopes like uranium-235 has much higher probability to cause fission, therefore served as nuclear fuel in the reactors. However, the even atomic mass number isotopes such as uranium-238 has much higher probability to capture the fast neutrons to be converted to odd number nuclear fuel, such as uranium-238 converted to plutonium-239, thorium-232 converted to uranium-233. So far, all the commercial reactors are thermal reactors. Therefore, for fuel sustainability, the next generation 4 fast reactors must be developed. Nuclear fusion reactors primarily use the fusion reaction of deuterium and tritium. Deuterium can be extracted from seawater, and the energy released from the deuterium in 1 liter of seawater through fusion is equivalent to that of 300 liters of gasoline. The deuterium in the world's seawater is enough to sustain humanity for tens of billions of years, offering a permanent solution to energy needs. Tritium can be transmuted from lithium. However, the fusion reaction rate is highly dependent on temperature, generally increasing dramatically as temperature rises. Nuclear fusion reactors must operate at temperatures exceeding 100 million degrees centigrade, roughly 7 times hotter than the core of the sun, to achieve a sufficiently high reaction rate that produces more energy than it consumes. So which creates huge engineering challenges.
Yeah, we often see the term artificial sun when discussing nuclear fusion, but to many, this sounds like something out of science fiction. So, could you explain what an artificial sun actually is?
Artificial sun is really a nickname for nuclear fusion reactors.
Hmm.
Fusion is the process that powers the sun. In the sun, hydrogen atoms collide, fuse into helium, and release extremely large amount of energy. On Earth, scientists try to recreate this in the fusion reactors. The name artificial sun comes from this attempt to simulate the physics of the sun, but in a controlled manner.
China's East reactor recently kept plasma stable at extreme densities, breaking the so-called Greenwald limit. And for listeners who aren't familiar with nuclear science, the Greenwald limit is basically a speed limit for fusion fuel. But why is breaking this limit such a game changer for nuclear fusion research?
Yeah. The Greenwald limit is an empirical rule which describes the maximum plasma density that can be stably maintained in a fusing device. Exceeding this limit, the plasma usually collapses, leading to energy loss or even damage to that device. For decades, this was seen as a hard upper limit. Recently, China's yeast device managed to keep plasma stable beyond this limit. Higher plasma density means more fusing reactions happening in the same device, and more energy can be produced. Such a breakthrough could enable future fusion reactors to operate with fuel densities nearly twice as previously thought possible.
Yeah, so if in the future, if nuclear becomes safe, flexible, and cheap, could it finally displace coal and gas completely? And what could that mean for global climate goals?
If nuclear energy, whether fission or fusion, becomes safe, flexible, and affordable, it could indeed displace coal and gas almost entirely. And nuclear produces nearly no greenhouse gases during operation, and it is stable and weather independent. It will make net zero carbon targets far more achievable.
Yeah, but I think one of the problem is that public perception of nuclear energy has long been shaped by fear and skepticism. So, what would it take to build public trust and make nuclear energy widely accepted again?
Public perception of nuclear energy came from accidents like Chernobyl and Fukushima, and from concerns about radioactive waste and leakage. To rebuild trust, several things are essential. First, improving the reactor safety with new technologies, such as using passive safety systems. Second, uh, finding credible long-term solutions for waste management. Third, transparency to public. Nuclear industry must communicate openly and honestly with the public about risks and safety measures, while also making nuclear science easy to understand. Trust will grow when nuclear is seen not as a threat, but as a safe, reliable ally in fighting climate change.
Yeah, and since we still have some time left, I think maybe we can go back and look at this goal of tripling nuclear energy by 2050. So can you kind of give us a picture of what would that look like in practice?
I think nuclear overall will play a significant role in the overall energy package because nuclear offering stable, weather independent baseload power, unlike traditional renewable energies such as solar and wind, they are very intermittent, not stable. Especially for the digital economy like AI data centers, they need a very stable baseload. They cannot afford to downtimes. In China, the nuclear share currently in the overall electricity package is still very small, only 5%. So you just think the whole world in average is about 9 to 10%, and in advanced developed countries, the share even much higher, like France, 65% their electricity is from nuclear, and USA almost 20% is from nuclear energy. So there is big potential for China nuclear sector to grow.
Yes, yes, indeed. But what do you think could be the biggest uncertainty that could possibly derail this nuclear expansion? And I mean, not just in China, but like globally.
Globally, I think the first thing is safety. We need to make sure the nuclear reactors will, run safely. Another Fukushima or Chernobyl cannot happen. If it happens, it will definitely, put the nuclear energy back.
Yes.
And also another big factor is how to manage the waste, nuclear waste. It is you need a lot of research and development to well manage, these kind of radioactive wastes.
Yes. Okay. Thank you, Professor Zhao. Thank you so much for joining us today.
Yeah, thank you so much. Yeah.
And that wraps up this edition of Climate Watch. You can find more episodes on your favorite podcast platforms. Just search for Climate Watch and hit subscribe. Don't forget to leave us a quick review or share it with a friend. You can also email us at radio@cgtn.com with your questions or feedback. And stay updated on the latest climate stories with our Substack newsletter, Climate Choices. I'm Zhao Ying. Thank you so much for listening. See you next time.